B.3 Fibonacci numbers. So this is the last video of this part. In this part, let us look at the well-known Fibonacci numbers. I think you already know these numbers, but we can learn a lot of things. The definition of this kind of numbers very simple. But when we work on it, when we solve the problem finding Fibonacci numbers, so there are a lot of interesting theories we can learn. All right, so let us start. First, let us look at the problem first. Our problem number 11, calculate Fibonacci numbers. Given recursion formula, initial values to F0, F1 values, then this simple recurrence relation, Fn equals Fn minus 1 plus Fn minus 2. So simple, right? But a lot of interesting properties behind this kind of numbers. All right, find the Fibonacci numbers F sub n. Here we can use the recurrence formula to calculate first a few Fibonacci numbers, like this. If you try to find some rules, it is not easy to see any simple rule from it. If you just look at the numbers, can you find some simple rule? It is very hard, right? All right. Let us look at how do we plan to solve this problem. All right. We have two plans. Our first plan, we solve it algorithmically, using our computer algorithms. The first way. And we need to write a program to implement our algorithm. Although we may have several ways to do it. So we may have different methods to solve this problem. But the whole thing, if we solve it using computer algorithms, that's the first approach. Then the second, solve it mathematically. Is it possible we can find a mathematical formula? F sub n. So this one, we can write it as a math formula. How about that? That will be very nice. Because if we have an explicit formula, when we do the calculation, we just plug in the variable value in this formula. Then we just do calculation, straightforward calculation, then we can find the answer quickly. How about that? Because if we use math formula, probably we can get a faster calculation. So that's the second approach. But the key of the second approach, you need to derive a math formula. That is pretty hard. All right, so let us take these two approaches. First, the first approach, let us, forget about the formula, right? Forget about the formula. Let us just calculate the Fibonacci numbers from the recurrence relation directly. All right. Here, because the recurrence relation is given, if you want to write a formula, write an implementation function code, pretty straightforward, right? The recurrence relation already given. You just write a straightforward function using recurrence relation, you can get an answer immediately, right? Yeah. So our first solution, the definition of this function. How about that? Fibo. Yeah, let us call the function name Fibo. Fibo of integer n, input value n. Yeah. Then, based on the definition of the Fibonacci numbers, two base cases. If the first base case, n less than or equal to 0, yeah, then second base case equals 1, yeah, trivial, right? Two trivial cases. Then the main case, main non-trivial case, return the value expression is generated, is, represented using recurrence relation. Fibo of n minus 1 plus fibo of n minus 2. How simple it is, right? How easy it is, right? Yeah. Then this problem can be solved in this way correctly. Yeah. Based on a definition. How can you say it is incorrect? Nobody can say it is incorrect, right? Yeah. Here, the correct here, it means the answer produced by this function is correct. Okay? Nothing to do with the efficiency. How fast this function can produce the correct answer, we don't know. We just know this function will produce the correct answer. All right. Yeah. All right, but the next question, we like to know if this method is good or not. If this implementation is acceptable or not, right? Yeah, that's the next important question we need to answer. All right, so here, first, let me give you the answer. All right, yeah. First, let me give you the answer. Yeah. It is a horrible implementation. The efficiency, the performance is extremely slow. Extremely slow. How can we see that? We cannot hear from the code. Nobody can see that, right? Extremely slow. Yeah. But if someone likes to do some experiments, then you will see it is very slow. Okay? Yeah. For this reason, I may like to give you this problem as our project number 2, calculating Fibonacci number. So that will be our project 2. You will see how slow it is. Yeah. Yeah. We will use 3 different methods. 1, 2, 3. 3 different methods. Okay. So you will compare which one is the best, which one is the worst, and so on. Similar to our project 1, right? Project 1, you are given 3 different methods. Then you write a code to implement all 3 methods. Then you compare the efficiencies, right? Yeah. Here we will do the similar things, but the problem is Fibonacci number problem. Okay. All right. Yeah, here, let me explain the project plan. Yeah. Compare efficiency for 2 different algorithms. Yeah, so this is the first one, but there is another one, right? Yeah. But other than that, we may have another interesting algorithm given in our textbook. We have third one. Yeah. So 2 different given in this lecture, but third one not given in the lecture. All right. So there is third one. third one, that's in textbook, in our textbook. Because that solution is very special, very, very special. So I like to also include the third solution, third solution into this project. In that way, you can learn a lot. All right? All right, yeah. Next, how bad is the algorithm? Because we want to understand how bad it is, right? I need to explain why it is bad. Yeah, so here I need to do that. Yeah, I do not want to delay that question, the question of that answer to the project time. When you work on the project, you get a real world experience on that. So before you work on the new project, I want to give you some idea why it is so slow. That's easy, pretty easy to explain that kind of idea. Can we improve it? If you understand why it is so slow, then you can design a new algorithm to improve it. Yeah. All right, so let me explain why it is so slow. Here, I just use a simple diagram. You can get the answer quickly from this diagram. Yeah. All right. When we start, I want to draw a recursion tree. Yeah. Because when we implement recurrence relation, when we call a recursive function, the way we calculate the function can be described using this recursion tree. Yeah. So let me draw a simple example for you. Yeah. Let me just use a fiber of 6. It's a pretty small number, right? Fiber of 6. That is a pretty small number, but it is already good enough to understand why this method is so slow. Yeah. When we start, in order to find fiber of 6, you need to get the value of fiber of 5 and a fiber of 4, right? Then, in order to get fiber of 5, you need to have recursion another time, right? Yeah, fiber of 4, fiber of 3. Yeah. Similarly, fiber of 4, you need a fiber of 3 value and a fiber of 2 value, right? And so on. Yeah. So we can keep doing things like this, going down from the tree along all the possible branches. We do things like this, okay? Eventually, you get a pretty big tree, right? Yeah. Pretty big tree. Like this. Yeah. Now, when you see this tree, can you get an idea why this recursion method is so slow? Can you see that? Try to look at the tree. What property can you see from the tree? Okay, yeah. Here, let me point out the biggest problem in this tree. Yeah. That is, some of the nodes are repeated many, many times. Here, let's look at fiber of 2. How many times fiber of 2 is repeated? See? So many times. Here, 5 times. Now, in this small example, you need to calculate fiber of 2 5 times. Think about, if you calculate fiber of 100, can you imagine? We can calculate fiber of 100. Much bigger than 6, right? Yeah, 100. Yeah. How many times certain fiber number certain smaller Fibonacci number will be repeated. Can you get that idea? Right? Many, right? Many. We know some Fibonacci numbers have to be repeated many, many times. That's the reason it is so slow. So the conclusion is too much redundant calculation in this method. Redundant. Why we need to calculate the same number 5 times? Can we just calculate once? Then the other 4 times, we do not do the redundant calculation. Can we just use the existing value directly? Right? So that's the key observation we have here. Key observation. All right. So based on this key observation, next we can get a better solution. All right. So let me describe our method number 2. Greatly improved the solution. All right. How? Method 1. Regarding improvement, we have 2 methods. 2 different methods. All right. Let me quickly describe it. The first one, iterative algorithm. We do not use recursion. We use iteration. In that way, we can avoid redundant calculation. All right. The code is like this, using a for loop. In this way, can you see any redundant calculation? No, we cannot, right? Each Fibonacci number of smaller size is only calculated once. How about that? No redundant calculation. So this method should be very fast. Okay? So you can see that. Second, we apply recursive algorithm without redundant computation. All right. We do not want to throw away the recurrence formula. We want to use it. All right. But we want to avoid redundant calculation. Why? Later I will explain. Here, let us look at method number 2 first. Use an array to store calculated values. Each value we only want to calculate once. After the calculation, we just store it in an array, in one element of the array, to avoid redundant calculation. That's simple. All right. Make sure that no value is calculated more than once. If we can implement these 2 points, then we avoid redundant calculation. So we can improve our algorithm much faster. All right. So let us look at the implementation. To calculate Fibo of n, we define an array f of n. F array with n elements. All right, with n elements. The size is n. Then we define a function like this. Can you see anything special here? You can see, comparing with our, previous 2 implementations, we need more lines, right? Yes, we need more lines. You can see we need to use an array called non-F array. Non-F array. So from the name, you can see this array is used to store the non-Fibonacci numbers. Non-Fibonacci numbers. But this array initially, all the values of the elements are 0. Initialization, all 0 values. Yeah. All 0 values means unknown. Yeah. All the Fibonacci numbers from 0 through f of n, or n minus 1, whatever, all unknown. All right, yeah. So after that, yeah, 2 trivial base cases, that's simple. All right. Then the key part, these 2 lines, the main part. If I greater than 1, S, a new variable S, equals fibo of I minus 1 plus fibo of I minus 2. Recursion. So this line, you can see we still do recursion. All right? We do not avoid recursion. We still do recursion. Yeah. But when you do recursion, you only need to add an extra line. Try to understand the logic. Yeah. Try to understand the logic. All right? Yeah. Return f of I equals S. All right? So after you get an S, you assign it. This is assignment, right? You assign it to known f array of I. After you do the assignment, you return as the function value. All right, yeah. But after you have that, so this line is important. The calculation, main calculation part, this line is important because the next time when you need to use one of the smaller Fibonacci numbers, you do not need to go through all the recursion, because when you hit this line, if known f of I greater than 1, you just return the known value immediately. You do not need to go down below all the lines below this line to do a lot of calculation. You don't need to, because you already have the value, just return it. This method is pretty smart. Pretty smart. Yeah. In this way, we ensure no Fibonacci number is calculated more than once. Yeah. But it is true we need to do a little more work than the method 1. Yes, it is true. We will do a little more work than method 1. Yeah. But still, the idea is valuable. The idea of this method is valuable. Why? Yeah. So let me explain in a few sentences before we finish this video. Because this method corresponds to a very important algorithm type called a dynamic programming idea. So that is the topic of chapter 8, dynamic programming idea. So this method is extremely important in computer algorithms. Dynamic programming. Yeah, it's a big topic. Yeah. For this class, we may not have that much time to learn that topic. The good thing is we understand that concept, idea, right here when we solve Fibonacci numbers. Yeah. So the essence of this dynamic programming method, no repeated calculation. When you need to use previous older values, if they have been calculated before, you just retrieve from storage somewhere. The storage somewhere, there is a name for it called a dictionary. In that dynamic programming, we use a special terminology, a dictionary for storage, for temporary storage dictionary. We just look up the value from the dictionary. Here, so this known F array, we treat it as a dictionary. When we need to use a value in the array, we look up in the dictionary first. If we can find it, we use it. If we cannot find it, if it is 0, we cannot find it, then we do the calculation. We do the, recurrence relation calculation. Yeah. All right, let us complete this video, and here we have seen 3 different algorithms calculating Fibonacci numbers. In part C, we will learn more knowledge about Fibonacci numbers. All right, so let us start part B right here. Yeah.